Probability is something that most of us are pretty familiar with, at least the basic stuff. So hopefully most of what we're doing today is a review. It's kind of fun also. Our two learning goals is I can find sample spaces. We'll define what that is and show you how to find it. And I can find experimental and theoretical probabilities. So we'll go over the difference between those two. There's going to be lots of definitions here. So at any point, if you need to pause it, you can pause it and write these down. There's a lot of vocabulary that you need to know with probability. The first one is the probability experiment. It's simply an action or a trial that has varying results. For example, I can roll that dice, right? There's different results or outcomes. Outcomes are the possible results of a probability experiment. So when we say what are the possible outcomes, you're just finding out what all the possible results can be. An event is a collection of one or more outcomes. So an example, an event could be, I roll the dice and get an even, right? There's 3 outcomes to that event, the favorable outcomes, 2, 4, or 6. Okay, in sample space, this is our learning goal, right? So find a sample space. Sample space is the set of all possible outcomes. So if we're rolling that dice, right, my sample space would be every possible outcome I could get. So I could get a 1, 2, 3, 4, 5, or a 6. Those are my possible outcomes. Okay, this one says you flip a coin and roll a 6-sided dice. How many possible outcomes are in the sample space? And then list the possible outcomes. I'm going to show you a quick way to find that. An easy way to find the possible outcomes is to make a tree diagram. So you start with your first event. It says you flip a coin. So if I flip a coin, I could get a heads or I could get a tails. If I get a heads and then I roll the dice, I could get a heads and a 1, a heads and a 2, okay, so there are 6 possible outcomes. I'm going to list them here. Heads 1, heads 2, heads 3, heads 4, 5, and 6. So there's some of my possible outcomes. I could also get a tails first and then get a 1, 2, 3, 4, 5, 6. So these are my other outcomes. So this is my sample space. Those are all the possible outcomes. It also asks how many possible outcomes there are. Right, there's 6 and 6, so a total of 12. So there's my sample space. That's how many outcomes are in my sample space. I want you to notice something there, right? For the first event, there were 2 possible outcomes. Then I rolled the dice. For the second event, there were 6 possible outcomes. So for each of these, there are 6. So in other words, 2 times 6 equals 12. Okay, 12 total possible outcomes. So keep that in mind. That will be helpful for us. I want you to try these two. So find a sample space, find a number of possible outcomes. So pause it and do that, and then come back and we'll go through it together. If you flip 2 coins, get heads, tails. You get a heads and another heads, or a heads and then a tails, or I could get tails first, and then a heads second, or a tails first and tails second. So if you follow that mapping, right, my possible outcomes I have heads, heads. A different outcome would be a heads and then a tails. Oops. Heads and then a tails. I could get a tails heads, or I could get a tails heads. So how many possible outcomes? There's a total of 4. What is my sample space? It's right there. There's 4 things in it, but that's all the possible combinations or outcomes that you can get there. Again, I want to point out the first event right there, right? It had 2 possible outcomes, right? You flip a coin. The second event, flipping a coin, the other coin, there's 2 possible outcomes. 2 times 2 equals 4. So you kind of think of a shortcut way of finding the possible outcomes. Hey, flip 2 coins and roll a 6-sided dice. I'm not going to make the tree diagram for this one. It's going to be really big. It's going to look something like this, right? Heads, tails. Then for the second event, heads, tails, and then you're flipping a coin. So for each of those, there are 6. So to count it, there's 6, 6, 6, 6, so 24 possible outcomes. Or if you look at it, right, you flip a coin, there are 2 outcomes. Flip another coin, there are 2 outcomes. Roll a 6-sided dice, there are 6, right? 2 times 2 times 6, that gives you a total of 24. If you were to actually list the sample space, it could be like, for example, heads, heads, 1, heads, heads, 2, all the way to 6, then heads, tails, 1, heads. So you can kind of think about how you do that tree diagram if you're doing that. Okay, some more definitions. So the actual probability of the event. Okay, this is, make sure you have this written down. The probability of the event is the measure of the likelihood or chance that the event will occur. Probability is a number from 0 to 1. It includes 0 and 1. Okay, and you can write probability as a decimal, fraction, or a percent. I don't care which way you write it, unless you're specifically told to write it one way or the other. So if you look at this, right, if we have a probability of 0 over here, that means it's not going to happen. It's impossible. I don't know, see like pigs grow wings and fly. Not going to happen. Certain, 1, I used to always say in class that, you know, I'm 100% certain we'll have class tomorrow, but nowadays I guess it isn't certain anymore. It's not a probability of 1. If you look at this, if you're in the middle, like 1 out of 2, 0.5, 50%, equally likely to happen or not. If you're over here somewhere, right, over here somewhere, it's unlikely. If you're over here somewhere, then it's likely. You know, it's greater than 0.5 or a half. And you guys are pretty familiar with this. You've seen this before. The first type of probability we're going to talk about is what's called theoretical probability. Theoretical probability is when you find a probability without actually trying the event. So the way you do that is you take the number of favorable outcomes. Favorable outcomes is you end up with what you're trying to get. And then you take that out of the total possible number of outcomes, and that gives you the theoretical probability. This is just notation. If I want to find a probability of the event A happening, this is the shorthand way of writing it. That way I don't have to write out the probability of this happening. I can say P of parentheses A. So just know that notation. That's the notation our book uses, and that's really common. Most textbooks use a similar notation. So here's an example. Students taking a quiz randomly guesses on the answers to 4 true and false questions. What is the probability of the students guessing exactly 2 correct answers? So one approach to this, an easy approach, is to write out the sample space. So let's say the student first guesses on question number 1, and he can either get the answer correct or he can get the answer incorrect. Okay, and then you go on to the second one. He could get the first answer correct and the second answer correct, or the first answer correct and the second one wrong. So I'm using C for correct and I for incorrect. Same thing over here. There's 2 questions. We got to keep going. He takes it. There's 4 questions. So, right, it could be if he guesses correct, he get correct or incorrect. Those are equally likely. Correct, incorrect. I'm going to run out of room here fast. Okay, let's keep going. This is my 4th question. This is getting a little messy here, but okay. First of all, we need to find the total number of outcomes. So you can count all these across the bottom. These are going to tell you the total number of outcomes. You can count all the way across. The other way we could have done that, right, is there are 2 possible outcomes in each of those, and there's 4. So really it's 1, 2 times 2 times 2 times 2. So it comes out to be 16. You can count across the bottom, and there are 16 possible outcomes. So that's going to be when I find the probability of getting what is probably the students guessing exactly 2 correct. So we know there's 16 possible outcomes. What I need to do is just count how many of those have 2 correct answers. So this gets a little bit tricky. I need to follow. I'm going to follow these strings up. This one has 1, 2, 3. That one's out. This one has, let's see, there's an incorrect. There's 1, 2, 3. That one's out. This one has 1, 2, 3. It's out. This one has incorrect, incorrect, correct, correct. And there's 1 right there. Let's just keep track of these 2 tally marks up here. Let's do the next one. 1, 2, 3. Oh, sorry. 1, 2, 3. That one's out. There's 1, 2, there's another one right there. Okay, correct, incorrect, incorrect, because there's 2. That one would work. 1, 2, that one doesn't, there's only 1 correct. Start over here. 1, 2, 3, that one's out. 1, 2, there's another one. Go over this next one. Let's see, we got correct and correct. There's another one. This one, there's only 1 correct. Start over here. There's 1, 2 correct. Then we got incorrect, no. But so it looks like we get them, there's 6. So there's 6 favorable outcomes. There's 6 times the student gets exactly 2 questions correct. And there's 16 possible outcomes when you just guess. Now that's written as a fraction, maybe a fraction of 3/8. If you want to, you can grab a calculator and divide that. 3 divided by 16 comes out to be 0.1875. So you can write it that way. If you want to write it as a percent, any one of those ways are acceptable ways of writing that answer. Okay, here's your next definition here. It says the sum of the probabilities of all the outcomes in the sample space out of P1. For example, if I roll a dice and I say what's the probability of getting an even plus the probability of getting an odd, that covers all the outcomes. Right? It either has to be an even or an odd. If I add those together, it's a half and a half, which adds up to be 1. That always happens. If you take the sum of all the different probabilities in the sample space, they always add up to be 1. So when you know the probability of event A, you can find the probability of the complement of A. Complement simply means it's the probability of A not happening. Here's a notation for it. So if, let's see, A consists of all the outcomes that are not in A and is denoted by, so the complement does denote this, you say that A bar, right? A with a bar over the top. Right? Complement of an event consists of all the outcomes that are not in A. So complement of getting an even is getting an odd. I say, what's the complement of rolling a dice and getting a 2? Well, the complement would be getting a 1, 3, 4, 5, or 6. Everything but a 2. So the complement. Here's the formula. If you know a complement, because the probabilities have to add up to be 1, I can go 1 minus the probability of A, and that tells me the probability of the complement. So as you roll a 6-sided dice, find the probability of each event. A says the sum is not 6, so I'm trying to find a probability. Let's say you want to find the probability of getting a 6, and then I can say what is. Let's try this up here. Let's try it this way. Let's say getting a 6. Probability of getting a 6 is A. That's event A. So not getting a 6 would be A bar. So you can do this either way. You can just find the probability of not getting a 6. So I'm actually going to start by finding the probability of getting a 6, which is, I'm calling event A. If you count here, there's 1, 2, 3, 4, 5, 6, 1, 2, 3, there's 36 possible outcomes. So what I do is how many of those actually add up to be 6. So if I go through there, let's see, there's a 6 right there. 2 and 4 will give me 6. 1 and 5 will give me 6. There's a 6. There's a 6. I think that's it. I think if we walk through there, everything else is going to be more or less. There's 1, 2, 3, 4, 5. So there's a 5 in 36 chance of getting a 6. Now, what's the probability then of the complement? What's the probability the sum is not 6? So that's probability to find the A bar, or the complement of A. All I do is go 1 minus 5 over 36, right? That'd be 36 over 36 minus 5 over 36. 36 minus 5 is what, 31. There's the actual question is, what's the sum of, what's the probability the sum is not 6, be 31 out of 36. So that just, to me, that's easier. By finding those 5 is easier than counting how many there are. So you kind of work backwards to find that. So B says the sum is less than or equal to 9. So let's find that. What's the probability of that? So we need to look and find out, maybe easier to find out the complement again, how many of them are greater than 9. So that's greater than 9, greater than 9. That one is 9. That one's greater than 9. Okay, I think those are all the ones that are greater than 9. So that would be, the probability of that would be what, 1, 2, 3, 4, 5, oh, 6 again. Actually, it was 5 last week, so not 6 again, but it is 6. That's the probability of getting one greater than 9. If you're getting one less than or equal to 9 is a complement. So that would be there's 6 out of 36 that are greater than 9. There are 30 out of 36 that are less than or equal to 9. So that one reduces, right? That would be, 5, 6 would be my probability. So kind of just thinking about what a complement is. Sometimes it's easier to find the probability of something by finding it's easier to find a complement and subtract it from 1 to find the probability. So you guys try this problem real quick, pause it, and then come back and we'll go through it together. So 3, you flip a coin, roll 6-sided dice. What's the probability the coin shows tails and the dice shows heads? So you could do the whole tree diagram, but instead I'm just going to figure out the total possible outcomes. Remember our shortcut? When you flip the coin, there are 2 outcomes. When you roll a 6-sided dice, there are 6 of them. So I times those together, that means there's 12 possible outcomes, right? If I picture my tree diagram, have 1, 2, and then true, heads, tails, and then there's 6 for each of those. What's the probability that it shows tails and the dice shows 4? So tails would be over here, right? So it shows the tails. Isn't there only one? There's only one outcome where you get a tails and a 4. So there's my probability, which is 1 out of 4. Hey, if I want to find the probability of A bar, all I do is go 1 minus 0.45, 0.55. That's how you find the probability of a complement. This would be 1 minus a fourth. So the probability of A bar equals 3/4. Hey, the probability of A is 1. The probability of its complement has to be 0. It has to add to be 1, right? The probability, this one's written as a decimal, that's fine. I go 1 minus 0.03. It's like 0.97. So find the complement is 1 minus whatever the probability is. Okay, the next thing we're going to talk about is experimental probability. Experimental, instead of based off logical reasoning, right, the favorable outcomes out of total outcomes, is experimentally you actually do the probability, you actually try it. So for example, if I ask you if I flip a coin, what's the probability of getting a heads, you would say, hey, that's 1 out of 2, because there's 1 heads out of 2 possible outcomes. If you're doing experimental, you'd actually flip that coin a bunch of times and keep track of how many heads you get, and you would base your probability off that experiment. So it's the number of successes, so in that example, the number of heads you get over the total number of tries. So here's an example. It says each section of the spinner shown has the same area. The spinner was spun 20 times. The table shows the results. For which color is the experimental probability of stopping on the color the same as the theoretical? So let's do the experimental first. So we look at my results down here. I did it 20 times. The probability of getting a red would be 5 out of 20. Red. I spun it 20 times. The probability of getting a green would be 9 out of 20. The probability of getting a blue, I got 3 blues out of 20. And the probability of getting a yellow would be 3 out of 20. Now let's know which one of those would be the same as the theoretical. So for theoretical, I'm looking over here, these are all equally likely, right? They're all the same size. So the probability would be 1 out of 4 for each of those. Right? Blue would be 1 out of 4, yellow would be 1 out of 4. That is my theoretical probability. So which is the same? Well, if I reduce this one, 5/20 reduces to be 1 out of 4. So the answer is the probability of getting a red would be the theoretical and the experimental cannot be the same. Which color is experimental probability of stopping on the color greater than the theoretical? That'd be this green one right here, right? The experimental is 9 out of 20. The theoretical is 3, sorry, not 3, it'd be 1 out of 4. Which if you get a common denominator, that means that would be 5 out of 20. Right? The experimental is greater than the theoretical, which you got over there. This was based off a survey that's really similar. In the United States, a survey of 2,184 adults aged 18 and over found that 1,320 of them have at least one pet. Types of pets these adults have are shown in the figure. What's the probability that a pet-owning adult chosen at random has a dog? Okay, so this is only talking about those that have pets. So how many total are there? It tells you up here the survey had a total of 2,184. So if I was going to randomly select one of those 2,184, what would be the probability that they have a dog? Well, how many of them had dogs? 960. Okay, there's your answer, and you could leave it as a fraction. We'd probably reduce that. A lot of times, probability is easier, especially with big numbers like that. It's easier to look at as a decimal. So if we change it to a decimal, it comes out to be approximately 0.42. So about 42% or 0.42 is what it comes out to. What's the probability that a pet-owning adult chose a random owns a fish? You guys figure that out real quick. 146 over, what was the total again? 2,184. If you want to write that as a decimal, comes out to be approximately 0.07, or about 7%. Okay, last thing, odds. The odds of the event compare the number of favorable outcomes and unfavorable outcomes. So notice down here, this is the difference. This is, instead of being the total outcomes, it's the unfavorable outcomes. If you want to find the odds against, you just do the odd, you just flip-flop those two. Take the number of favorable, unfavorable outcomes compared to favorable outcomes. So find the odds in favor of stopping on the yellow. So the way we do that is, how many yellow sections are there? There's 1. How many are not yellow? 3. So you write that as 1 to 3. A lot of times odds you'll see written that way, 1.3. Again, 1 represents the favorable outcome, and 3, instead of being the total outcome, is the unfavorable outcome. So instead of being 1 out of 4 probability, when you do odds, it's 1 to 3. 1 favorable, 3 unfavorable. So here's a little tricky question. It says, what's the probability of winning a balloon dart game? Well, the probability of winning a balloon dart game is 1.2. The odds of winning a ring toss are 1 to 5. Which game gives you a better chance of winning? So just be careful. These are two different things. This one is probability. This one is probability. This one is odds. So we need to make them the same. So let's make them both probability. So the probability of winning the balloon game is 0.2. I'm going to write it as 1/5. The probability of winning the ring toss well, the odds are 1 to 5. So that means 1 favorable outcome, 5 unfavorable. So altogether, there's 1 favorable outcome, and there's a total of, if I add those, we get the favorable 1 and the unfavorable 5, would be a total of 6 total outcomes. So the probability is 1 in 6. The odds is 1 to 5, favorable to unfavorable, but the probability is 1 to 6. That's a total, that's a favorable outcomes to the total. So which one gives you a better chance? Well, 1 in 5 is bigger than 1 out of 6. You can change them both to decimals if you need to, but the answer would be the balloon dart game. The last one says an example 4, find the odds against stopping on the red. So let's go back to that little chart. The odds against stopping on the red. So since we're finding the unfavorable outcomes, we'd say how many unfavorable? There's 3. How many favorable outcomes? Okay, it'd be 3 to 1 would be that. So you have favorable outcomes to unfavorable, or if you're trying to find, you can do the opposite. You can find the unfavorable and the favorable. A lot of this you're familiar with, but it's going to be building vocabulary, it's going to be mental notation, so it should take time and take some good notes to make sure you get all that down. This will give you the basis for what we need for the rest of this chapter.